Hi. So, hello everyone. Hope I am audible to you. I'm Piroto and I'm the co-founder and director of IREES. Today, me and will be your host. Now, he's a structural geologist and he is a mentor of IREES and critical natural science through such support. Our seminar series EPS3 activity. Hope you enjoyed our previous lecture on Mars, Moon, and then machine learning applications in astrophysics. Today, we want from of IRIS you everyone. If you have any questions, feel free to write in the chat box during the seminar or after the seminar, and please turn off your videos and microphone off during the session. Now, without wasting my time, I would like to invite Narayan to start hosting the session. So, thank you, thanks for joining us today. Narayan, now the stage is yours.
Hello, Priyabrata. Thank you. Am I audible?
Yes, you're audible.
Oh, okay. Thank you. So, good evening, everyone. Today we are here again to attend another nice seminar, and this time we have with us Dr. Gourab Bhattacharya from the Tennessee Tech University. He is currently an assistant professor there. And before the joining this position, Gaurav did his BSc from Dadin Presidency College, Kolkata. Then he did his MSc from IIT Bombay, and then he did his PhD from the University of Alabama. So Gaurav has his own interest in the domains of structural geology, tectonics, geodynamics, sedimentology, as well as geochronology. And this is well reflected in the diverse publication profile of Gaurav. So without wasting much time, let's hear it directly from Gaurav. Gaurav, welcome.
Hi Narayan, am I audible? Can you hear me, Narayan? Can you please confirm if you can hear me?
You're audible.
Okay, all right. Just a moment. All right, so second.
Yes, things are all right.
Okay. Okay, hi everyone. Thanks, Shubham, for sharing a very cinematic introduction before the seminar. Thank you for inviting me here for this webinar today. I'm happy to be among you and very excited to share my research with you all. So, like Narayan mentioned, my specialization in geology encompasses a broad spectrum from observing minerals at the microscopic scale. Just a minute. From observing minerals at the microscopic scale to understanding very large scale geologic processes operating in the continents. In other words, I basically study minerals to learn about the geologic processes associated with mountain building. The two main physical properties that my research usually focuses on are temperature and time, hence the two words thermal history on the title. Now, in general, geologic processes like subduction, deposition, faulting, etc., these processes move rocks through a range of depths inside the earth. And as the rocks move through a range of depths inside the earth, they experience changes in temperature. The central theme of my research so far has always been about determining the time temperature history or the cooling history of rocks in mountain belt type of settings, and then to identify the key geologic processes that moves rocks upwards towards the surface through the Earth's thermal field over time. These geologic processes that move the rocks upwards through the Earth's thermal field over time are known as rock exhumation processes. So in general, when I start my research, there are some questions I typically ask myself. So they are like, at what time a particular mineral or a rock was at a particular temperature inside the Earth's crust? How did it get to that temperature? What were the peak pressure temperature conditions experienced by the mineral? How did the mineral or the rock that was once buried deep inside the earth came up onto the surface where it is exposed today? Okay. Now, what's the importance of this kind of research? Firstly, this kind of research helps us to understand the overall cooling or thermal history of a mountain range. Okay. Now, if we try to understand mountains in terms of genetics, for example, then mountains are not inherently very different from each other. Okay. So for example, over here we have the Himalayan mountain range, which is geomorphologically bordered by the Tibetan Plateau. Likewise, if we look at the Appalachian mountain range in the United States, Appalachian mountain range is bordered by the Appalachian Plateau. If we go to the Andes mountain range, the Andes mountain range is bordered by the Bolivian Plateau. Okay, so so this kind of research helps to understand like the cooling pattern. If I can understand the cooling pattern in one mountain range, say for example the Himalayas, then I can take that understanding from a very young and active mountain range and try to apply it to see how the older mountain ranges like Appalachians or others evolved. So there is this aspect of comparative studies between mountain ranges to see how the thermal characteristics evolve in a mountain range, if there are similarities or are there any glaring differences. This type of research helps to identify some of the key geological processes that drives rocks upwards towards the Earth's surface. Are they tectonic causes? Are they geodynamic causes? Are they geomorphological causes? Or are they any climatic causes? In addition, this type of research also helps to understand if a region has been tectonically active in recent times. So how do I do this? The answer lies in a technique that is known as mineral thermochronometry. Okay. So minerals like zircons, apatites, biotites, muscovites, hornblends, they all act as geologic timekeepers. They preserve in them the information of time temperature history for millions and even up to billions of years. This record of geologic time in these minerals depends on a particular temperature, and as a result, these minerals are known as thermochronometers. The central question in thermochronometry is to identify when was the last time a particular mineral, let's call it mineral A, was at a temperature T degrees Celsius. Okay. So if we take this word thermochronometer and break it up, then the word therm means temperature, chron means time, meter is measuring. Okay. So in my research, I usually use 4 key thermochronometers. There are many other kinds of thermochronometers, but these are the main 4 ones that I use. The first one is apatite helium thermochronometer. Then we have the apatite fission track, the zircon helium thermochronometer, and the zircon fission track thermochronometer. As you see over here, each of these thermochronometer methods are characterized by a very particular temperature. So what does this mean in terms of like practical implications? So zircon helium thermochronometry basically tells us when was the last time a zircon crystal inside a rock was at a temperature of 200 degrees Celsius inside the earth. That's the temperature information. So how do we get the time information? This time information basically stems from the fundamental principles of how an element like helium diffuses inside a mineral crystal like zircon or apatite. And this nature of diffusion of an element inside a mineral crystal structure depends heavily on temperature. In this talk for today, we are not going to go into the details of the diffusion, but let's try to understand what are the practical implications of thermochronometry when it comes to analyzing mountain belts in general. So Zircon, minerals like zircons, apatites, they're common in igneous, sedimentary, and metamorphic rocks. In fact, in many of the igneous, metamorphic, and sedimentary rocks, we get chunks of zircons. So let's say like we have a mountain range over here, as shown in the cartoon diagram. Okay, you can think of it as the Himalaya, the Appalachian, Andes, it doesn't matter. Okay, so let's say like this mountain range over here is made up of granite. Okay, so somebody goes into the field, collects a granite sample, and analyzes the zircon helium age of this granite. Let's say that age comes out to 100 million years. What does that exactly mean? So that means that the last time a zircon crystal inside that granite was at a temperature of 200 degrees Celsius was about 100 million years ago. Now, let's say somebody also determines the apatite helium age from the same granite sample. Let's say that age comes out to be 90 million years. What does that mean? That means that the last time the apatite crystal inside the granite was at a temperature of 60 degrees Celsius was about 90 million years ago. Now let's take these two information and try to understand the overall thermal history of this mountain range. So the granite sample had a zircon helium age of about 100 million years. It also has an apatite helium age of about 90 million years. So to sum up, this granite sample moved from a temperature of 200 degrees Celsius to 60 degrees Celsius in 10 million years time. So that translates to a temperature difference of 140 degrees Celsius over 10 million years. So that means a cooling rate of 14 degrees Celsius per million year. Now, if we know the geothermal gradient in this mountain range, okay, let's say for the sake of argument, the geothermal gradient is 35 degrees Celsius per kilometers. Then if we divide the cooling rate with the geothermal gradient, then what we get is called the exhumation rate, which turns out to be 0.4 millimeters per year. This value, the exhumation rate, is basically what that tells us the rate at which the rocks are coming upwards in a vertical direction towards the Earth's surface over time. In a nutshell, this is what mineral thermochronometry tells us. So now let's take this understanding and apply it to a real world scenario where we use multiple thermochronometers to understand the thermal history or the cooling history of a mountainous region. And that mountainous region is in the Himalaya and was a key part of my PhD study area. Now, before we dive in to the overall to interpret the cooling history of a mountain range like the Himalaya, it's best to have some idea about how the Himalayas came into being, or like the overall broad geologic history of the mountain. So like the organizers first showed in the very beginning, the Himalayas, like this is the present location of the Himalaya. It's sandwiched between the Indian plate in the south, the Asian plate in the north, but this was not the configuration, or the plate tectonic configuration about 100 million years ago. About 100 million years ago, there existed a giant ocean called the Tethys Ocean that separated Indian plate from the Asian plate. Then the Indian plate accelerated northwards and collided with the Asian plate to form the Himalaya and the Tibetan Plateau at about 50 million years ago. This collision closed the Tethys Ocean that once existed between India and Asia. The Indian plate started subducting under Asia and has been continuing to do so till today. Now, the zone of welding between the India and the Asian plates is known as the India-Asia Suture Zone. It's also known as the Indus-Yarlung Suture Zone or Indus-Sangpo Suture Zone, based on the two largest river systems of Asia, the Indus and the Brahmaputra, or the Sangpo River, that drains parallel to the suture. So my study area, or the focus of my research, was the Indus Basin in Ladakh in the northwest India, which lies at pretty much the heartland of the India-Asia plate collision zone. The goal was to determine the cooling history of the Indus Basin using zircon and apatite thermochronometry, and to identify the key geological processes that drove exhumation along the India-Asia plate collision zone. So it all starts with field work. Okay, so just to give you a field perspective of the region, here I am standing on the Asian plate, looking southwards. This is the Indian plate with, in the south, the snow-capped mountain ranges. That's the Indian plate. Over here, I have the Indus Basin sedimentary rocks right in front of me. This is the Indus River that flows almost parallel to the suture zone through this region. Over here, the Asian plate is the overriding plate. The Indian plate in the south, that's the subducting plate. Now, these Indus Basin sedimentary rocks that we see over here, they were deposited about 50 to 26 million years ago, almost at or near sea level. But these rocks presently stand at extreme elevations of more than 4 to 5 kilometers. So how did this happen? How were the rocks that were once deposited at the sea level now have acquired such extreme elevations? This is a field snapshot from the Indus Basin. Okay. So the Indus Basin rocks are extremely folded and faulted. Just to give you a perspective of how big this structure is, here is standard electric light post. So this is basically the length or the height of a standard electric light post. And this is the overall complicated geologic structure that we see. So both marine and continental sedimentary rocks are found in the Indus Basin. We have conglomerates, sandstones, shales, coals, limestones, siltstones, everything. Now, previous researchers, when they studied the area, they tried to determine some maximum temperature values, and their values ranged between like 145 to 155 degrees Celsius. But when I started looking at the thin sections of these sedimentary rocks, what I found out was that many of these rocks showed varying degrees of recrystallization under the microscope. Now, recrystallization is a metamorphic feature. A temperature of 150 degrees Celsius was deemed to be too low to onset recrystallization on a regional scale. So I started doing what I usually ask. So I started asking myself, like, when was the last time a zircon mineral in a rock from the Indus Basin was at a temperature like 240 or 200 degrees Celsius? When was the last time an apatite from the Indus Basin was at temperatures of about like 60 to 120 degrees Celsius? Okay. So for that, I had to look at the general facies of the Indus Basin. So I started mapping the various rock units of the Indus Basin and started sampling rocks for thermochronometry. Usually, the rock that I mostly focused on was sandstones. Sandstones are generally rich in zircons and apatites. Here we have some folded sandstone beds from the Indus Basin. Here is an outcrop of conglomerates, shows an igneous clast, a sedimentary clast, a metamorphic foliated clast over here, all in the same outcrop. Eventually, a geological map was made from the region combining the major lithological and structural elements. Okay. So over here, you can consider the orange region as the Asian plate in the north. This white region is basically demarcating the Indian plate in the south. Everything that's sandwiched in between is basically belonging to the India-Asia plate collision zone. Over here, the Indus Basin, indicated by this cream-colored unit, is the thickest unit of the India-Asia plate collision zone. Mostly, I collected a lot of samples from various formations across various transects. Over here, only 4 such sample locations are shown for clarity. Most of the samples that were collected for mineral thermochronometry were coarse to fine-grained sandstones. Then I separated the minerals like zircons and apatites from these sandstones. This is how they look like after the separation. These are zircon crystals, been laid out on a grain mound. These are apatite crystals. This is how they usually look after they have been separated from the sandstones. Then I subject these zircons and apatites to a technique known as helium thermochronometry. So helium thermochronometry is the technique by which we measure the uranium, thorium, helium age of a mineral like zircon or apatite. Okay. Now, to the best of my knowledge, there are less than 50 labs all over the world that does this kind of analysis. I did most of my analysis at the Arizona Radiogenic Helium Dating Laboratory. This is housed at the University of Arizona, and this is what their instrumental analytical facility looks like. So this helium age is measured in combination by using a combination of two very sophisticated instruments. The first one is the quadruple mass spectrometer, which measures the helium content. Then we have the ICP-MS, which measures the uranium and thorium content. Once these contents are determined, we can put them into radiometric decay equations to determine the helium age of the zircon or apatite. So this is how a zircon crystal looks like when it is being irradiated in a laser chamber in this instrument. Okay. So once the helium ages are available, like this is what they looked like when I analyzed the ages from the Indus Basin. So what I found out was that all the zircon helium ages were between 20 to 9 million years. All the apatite helium ages from the sandstones were between 10 to 3 million years. Now, what does this mean? This means that the last time the zircons in the sandstones were at a temperature of 200 degrees Celsius inside the Earth was about 20 to 9 million years ago. The last time the apatite crystals inside the sandstones were at a temperature of 60 degrees Celsius inside the Earth was about 10 to 3 million years ago. So to combine these two results of zircon helium ages and the apatite helium ages from the sandstones, we can see that the Indus Basin rocks cooled from temperatures of 200 degrees Celsius to about 60 degrees Celsius between 20 to 3 million years. This coincides with the Miocene-Pliocene time in the geologic time scale. Now, it's important to remember that these Indus Basin sedimentary rocks, they were deposited between 50 to 26 million years. That's about like Eocene to Oligocene time. So these rocks were first deposited, then they were buried to temperatures exceeding 200 degrees Celsius, and then these rocks cooled from temperatures of 200 to 60 degrees Celsius between 20 and 3 million years. So that time, the Miocene-Pliocene time, there must have been some geological processes that must be operating that drove these rocks from temperatures of 200 degrees Celsius to 60 degrees Celsius, bringing them closer towards the surface. As we discussed earlier, these set of processes that brings rock upwards towards the surface are known as exhumation processes. And now is the time to look at some of the main geological processes that drive exhumation in the India-Asia plate collision zone. But before we do that, let's take a look at the bigger picture. Okay. So my study area in the Himalaya was in northwest India in the Indus Basin in this region. But the Himalayas are a huge mountain chain. They extend for more than 2,000 kilometers in northwest Pakistan, through India, Nepal, and South Tibet. Okay. So what I was trying to do was I tried to understand like how is this exhumation ages varying across the length of the India-Asia plate collision zone. So I started plotting various thermochronometric ages that were already published from the various suture zone units of the South Tibet. And then I compared with my data set from Northwest India. Interestingly, what I found out was that most of these ages that from the India-Asia plate collision zone were all more than 75% of them were Miocene in age. Okay, so this is a plot that shows the variation in age, the exhumation ages with longitude. Okay, so from 76 degrees, that's right over here, to about 94 degrees. That's the variation. And within this longitudinal stretch, more than 75% of the exhumation ages of the zircon helium, apatite fission track, all these ages turn out to be in the Miocene time span. So this is where things becomes interesting. So that means that the Miocene-Pliocene cooling signal that I'm getting in Northwest India is not just a local cooling signal that's operational in Northwest India. It is in fact indicative of a much large scale, in fact, a continental scale cooling event that was operational for more than 2,000 kilometers along the India-Asia plate collision zone. So what were the geological drivers of this Miocene cooling or Miocene exhumation? Now, Miocene is a very interesting time in the geologic history of the Himalaya or the geologic history of the suture zone or the India-Asia plate collision zone. Okay. So there were a lot of key geological events that were happening during the Miocene time all at the same time. Okay, there was a lot of subduction dynamic changes happening in terms of the Indian plate. There was a lot of thrusting going on in the region. The river started flowing with accelerated erosional rates through this region. And the Asian monsoon also intensified at around this time. We'll not go into all the details of these processes, but let's take a look at some of the key highlights of the geologic processes that were responsible for driving exhumation or producing these cooling edges across the widespread region of the India-Asia plate collision zone. So the first one is the geodynamic driver. So what happened in early Miocene time was that the India plate was subducting under the Asian plate. But in early Miocene time, this subduction dynamics changed. A part of the Indian continental slab broke off, and as a result, the remaining part of the Indian slab started pushing under the Indian plate. This underthrusting or pushing from below caused large-scale regional uplift of the entire region. So this explains the extreme elevations of more than 4 to 5 kilometers that we see in the Indus Basin rocks today. Now comes the tectonic driver. A lot of regional scale thrusting was happening in this region in early Miocene time. So over here, right at the contact between the Indian plate and the Indus Basin, we have the Great Counter Thrust. It's one of the largest thrusts in the Himalayan mountain chain. It extends for more than 2,000 kilometers from northwest India up to like South Tibet. And this thrust, the Great Counter Thrust over here, it was active in early Miocene time, and it brought older rocks from south of the suture on top of the Indus Basin rocks. So because of this thrust, the Indus Basin rocks were buried on to temperatures of more than 200 degrees Celsius. So this explains the elevated temperatures of 200 degrees Celsius in the Indus Basin. Okay, here is an example of a fault splay from the Great Counter Thrust that has moved into the Indus Basin. It transports older Indus Basin rocks on top of younger Indus Basin rocks. And lastly, we have the geomorphological driver, the Indus Basin that flows through this region in the modern day. It's a very old river. Back in Miocene time, it was flowing through this region, and it started eroding this region with extremely high erosional rates. Because of the accelerated nature of erosion through the suture zone in general, this removed like almost a vertical thickness of 8 to 10 kilometers of rocks in the Miocene time. So this Indus River erosion basically removed the cover rocks and exposed the deeply buried rocks that we see on the surface today. So if we summarize all the age results and the model results, what we get is basically a cooling rate that's about 11 degrees Celsius per million year, with an exhumation rate that's about 0.4 to 0.6 millimeters per year. This is the rate the Indus Basin rocks were coming up towards the Earth's surface during the Miocene Pliocene time. So to summarize these results, this research for the first time identified a Miocene Pliocene cooling signal along the India-Asia plate collision zone in northwest India. The cooling started from temperatures exceeding 200 degrees Celsius. This cooling signal is not just a local cooling signal in northwest India, it's also evident in South Tibet and is indicative of a much larger continental scale Miocene cooling event along more than 2,000 kilometers of the India-Asia plate collision zone from northwest India to southeast Tibet. What were the major drivers? So basically, what happened was there was a change in subduction dynamics of the Indian plate that caused a large-scale regional uplift that explains the extreme high elevations of the Indus Basin sedimentary rocks. Then we have the regional thrust tectonics affecting the region that led to the burial of the Indus Basin rocks to temperatures more than 200 degrees Celsius. And then the Indus River erosion that basically accelerated in the Miocene time removed these deeply buried rocks, almost like 8 to 10 kilometers of vertical thickness of rocks, thereby exposing the deeply buried rocks onto the surface. Now, this, for the sake of a very broad discussion, I kind of summarized all the information in a very simplified way. If you want to learn more about the details, you can check out some of the papers that came out from this region in recent years. But this type of study, like from using minerals like zircons and apatites to learn history of like continental collisions or history of or to understand geologic history of continents, it's not just limited to the Himalayas. This kind of research has gained pace in the last 10-15 years. And for example, here is an example of exhumation ages or cooling ages using zircon, helium, and apatite fission track analysis from the Andes mountain region. So in the Andes mountain region, this kind of technique helps to understand the thermal history of back arc basins, or like how fast were the plateaus being uplifted, things like that. It's also used in the Appalachian mountain ranges. Okay, so this type of technique is used in the Appalachian mountain ranges to understand the thermal history of the North American continent in relation to the opening up of the Atlantic Ocean. So these very tiny minerals can provide clues to massive or large scale processes that are operational during continental rifting or mountain building, for example. So before I sum up today's presentation, I'd like to tell you a very brief story. So this is a photograph that I took from the Shiok Valley. This is in the India-Asia Plate Collision Zone in Northwest India. This is a picture of the Death Valley in California in US. So both the mountain ranges in the Death Valley region and in the Shiok Valley region, they are formed by entirely different geologic processes. Okay. But there is something very fascinating about the mountains. Okay. So what happened is, like, for the same reason, this region acquired the name of Death Valley. That is, people who tried to cross this valley back in the 1900s with their mules and caravans, they failed to cross it because it's so arid, and hence the name Death Valley came into being. The Shiok Valley in this region in Northwest India also acquired the name because of very similar reasons. In local language, Shiok means death. So so when it comes to mountains, it's not just the geology that is always interesting. Sometimes the lived experiences of people in these regions share some commonality. Okay. So for the same reason, this place is called the Death Valley. This place in Northwest India, in the heartland of the India-Asia Plate Collision Zone, thousands of miles apart, acquired the same name. Okay. So the lived experiences of people also make it very, very interesting to understand, or like go into these places, do field work, and experience both the geology and the cultural side of doing field work. So with that, I'll end my presentation. Thank you very much for having me today, and I can now take any questions if Narayan has summed them up for me.
Yeah, thank you, Gaurav, for this nice presentation. More than a research presentation, I'd like to say that you have taken us to the classrooms again, and it was obviously a classroom kind of lecture with some case studies. So this is another way I can explain your seminar. So we'll obviously now go to the questions by our participants. And all the participants, they can use the chat box. If you are joining from Google Meet, You can use the chat box to write your questions, and those who are observing us from the YouTube live, they can use the live chat option also to write your questions. We'll try to answer them as much as possible. And at the same time, all the students, don't forget to fill up the Google form shared in this Google Meet chat. Okay, that would be required for the certificate distribution purposes. And now, me have a discussion with Gaurav. I had some questions in my mind, and you have obviously answered most of them. Still, I have something while I was checking your PPTs, that
Mhm.
these are the processes that is influencing what to say, plate scale or orogen scale processes, right?
Mhm.
Uh, Shubham Sarkar, could you please hear yourself? Oh, okay, Shubham. Yes.
Okay. Hold on.
Yeah,
Is
yeah.
it okay now?
Yeah, yeah, it's okay now. And if required, you can share it back if required,
Okay.
if you find necessary to answer the questions. So
Okay.
another thing is that what I was discussing, that we are discussing here orogen scale or plate scale processes,
Yeah.
and as we know that all the branches of geology, they are somehow interconnected.
Mhm.
Somewhere we find the connections between one domain with other, like that. So the students who are strictly not from this domain, what to say, they are not belonging to this tectonics or structural geology specializations or geodynamic specializations. They are doing research on some other topics or on some other specialization. How the
Yeah.
students can find this technique useful? Or in other way, I can frame my questions that what are the far field applications of this thermochronology analysis?
Okay, that's a very good question. And I'll take 1 minute to just share the presentation back again. I think I put
Yeah,
some
yeah.
slides just for application
Oh,
purposes.
okay, okay, okay.
Now let's see. Hold on a second. Okay. Okay. Can you see this? Yes. So, like,
Applications, yeah.
yeah. So like my research focuses on applications of thermochronometry in mountain belts, but thermochronometry has like a variety of applications, and the applications have only increased in last 5 to 8 years mostly. So, for example, this type of thermochronology is always like have been recently used in the hydrocarbon or petroleum industry. It helps to understand thermal maturity conditions in petroliferous basins. For example, what was the maximum burial temperature of a petroliferous basin, or like how did the thermal conditions evolve? Like this type of research is used in the Arabian Peninsula, in the Zagros Mountain Range, in the Appalachian petroliferous basins, in the South American basins. This has been a new direction of research. So over here are some recent papers that focuses on using thermochronology to understand hydrocarbon maturation or thermal maturations of sandstones, shales, the reservoir rocks, the traps, the seals, etc. Then it's also used in the mining industry to understand the thermal evolutions around the various kinds of deposits. For example, over here, these researchers use thermochronology to understand fluid flow and the hydrothermal alterations that are very important to understand porphyry copper deposits. Okay. So this type of research is also used in mapping geothermal anomalies. Okay, so let's say like if you have a hot spring, so I plan to do this in the Ladakh region near the Puga Springs to map geothermal anomalies, but I didn't get time. But that's also another thing. This is used by the energy industry people. So energy industry people, they're always interested in finding out alternative sources of energy. And to find out alternative sources of energy, it's important to have an understanding of what kind of geothermal anomalies exist in a region, how they can be mapped, and the potential way to map these temperature and time evolutions is using these low temperature thermochronometers. In addition, these thermochronometric techniques can also be used in collaboration with other techniques like stable isotopes, for example, to understand like paleo weathering conditions. Okay, so it's not just only limited to mountain belts. I also know like many of you have planetary geology backgrounds. So this type of thermochronometry has been recently used in dating any of the impact structures. Okay, so suppose we have an asteroid impact and we have a site that contains melts from an extraterrestrial object. So that melt structures can be dated and the thermal conditions of impact can be modeled using these type of techniques. So this has become a very utility-based technique to date impact structures that are recorded in the moon, for example, or other asteroid impact structures or at various impact sites. So the applications of thermochronometry are widespread. These are only a few that have come up in the recent years that I showed you. But there is a lot of potential in this technique, and it's only going to grow in the coming years.
Okay, that's extremely informative. I didn't know that this technique is being used in so many domains of geology. That's excellent. But at the same time, from your answer, another question actually popped up in my mind that you worked in Himalayan region where you mostly encountered high grade igneous rocks or metamorphosed sedimentary rocks kind of stuffs. And at the
Yes.
same time, just now while explaining, you have mentioned energy industry, oil industry, and mining industry. At the same time, planetary geosciences also. So the
Mhm.
fundamental question that comes to my mind is that how the sample is varying from domain to domain when I'm trying to use this technique of thermochronology.
Yeah, that's a good question. So like we have some, we call it like, it's like an index mineral. So we need some minerals, particular minerals to be present inside the rock so that we can use this technique. Okay, so most common minerals or the most traditional minerals that we have used so far are like zircons, apatites, okay, biatites, muscovites, hornblendes. These are also used. Then many recent researchers have been using materials like goethite, for example, or iron oxides. Okay, so as long as, so for like traditional research in the domain of geology, zircons, apatites, biotite, muscovites, these help a lot. These are present in like sedimentary rocks, especially siliciclastic sedimentary rocks. They're also present in a lot of igneous rocks, especially the quartz-rich igneous rocks. Okay. In some environments, these minerals might not be present. For example, in carbonate rocks. Okay, so if we have a carbonate environment, we have to look for a rock or the nearest rock that has a siliciclastic unit, because the proportion of zircons and apatites, they're like silicic minerals, their proportion tends to vary or go hand in hand with quartz. If the rock is rich in quartz, it is also logically should be rich in minerals like zircons, apatites, or other silicate minerals. So one way we do this is we try to identify, like in the region, if there is a rock that has the potential to carry these minerals. Okay, so we are always looking for rocks like granites, granitoids, gneisses, quartzites, sandstones, siltstones. Then there is also the factor of grain size. We cannot go below the sand sizes. Those zircon crystals should be large enough so that the laser beam can hit it and actually find out the time temperature information. So if it's like clay size, like for example, shales, or like phyllites or slates, then we can't use this technique. So it has to be coarse grained to some extent, sand size or upwards, and it has to contain some key minerals like either zircons, apatites, biotite, muscovite, iron oxides. And then we have to think of what exact problem we are going to answer. If it's a problem regarding, we are trying to understand the impact of moon, then zircons are enough. If we are trying to understand the thermal evolution of like a granite, for example, then we can use both zircon, apatite, as well as biotite, muscovite, and hornblende, all of which could be present in these rocks. Okay, so what these does is like each of these minerals, they have a very unique temperature that can characterize the thermal history. So if we have a series of minerals from one single rock, it basically tells you when was the granite at 500 degrees Celsius, when was it at 400, when was it at 300, when was it at 240, then 240. So we can basically construct an entire temperature time profile of the history of the rock using these methods. But the key thing is we need to have certain key minerals that we can use for this technique. We can't use it at all minerals. Does that answer your question?
Yeah, very elaboratively. And I think you can come up with another seminar to answer this couple of questions. Actually, you have gone to so much detail. I think you are kind of prepared to go for another seminar to answer
Yeah,
these questions.
yeah,
Okay.
I don't want to take much time, but yeah. So
Okay, okay, okay.
I can't see the questions where they're coming up. So if you can sum
So
up like what
yeah,
questions
yeah,
are there?
obviously I'll try. Okay, so I'll be telling you the questions and we can have a discussion session now. Okay,
Mhm.
so our participant Anushka Roy, the participant is asking why do we use apatite, zircon, or some specific minerals for determining age? Is there any specific criteria?
So when we are determining the age of from zircons or apatites or any, like we are looking for the uranium content, the thorium content, and the helium content. Okay. So what happens is like these minerals like zircons contain trace elements of uranium, thorium inside them. These are radioactive elements. They decay and they produce alpha particles, which is the helium. Okay. So what we are trying to measure is the parent to daughter ratio. Okay. But if your mineral does not have uranium inside it, it won't decay and it won't produce the helium. Okay. So zircons, we use zircons because zircons are very robust. Okay. Zircons are extremely hard. They can survive weathering, erosion for millions to even billions of years. Okay. So once a zircon crystal has formed, it can preserve the time temperature history in them for a long, long period of time in its pristine state. Okay. That's not the case with other minerals. For example, biotites. Biotites are easily degradable. Okay, or muscovites are easily degradable. So zircons are very useful because zircons can preserve that information for a long period of time. Also, zircons and apatites within their crystal structure, when they form from the magma, they incorporate uranium via the mechanism of substitution inside their crystal structures. Some minerals don't incorporate like uranium inside their crystal structure. So it fundamentally relates to like how a crystal grows and what kind of trace elements it incorporates inside its mineral structure when it closes and becomes a closed system, basically.
Okay, okay. Thank you for the detailed explanation again. And our next participant, Nirmala Chatterjee, is asking, is the Indus Basin within Trans-Himalaya? In your opinion, are cooling histories of gneissic domes in the Tethyan sedimentary belt and GHS in the south similar all along the Himalaya using method that you presented?
Uh, okay, so for the Trans-Himalaya is a very loosely defined term. It was defined way back in time. I don't remember the exact time when, probably in like early 1900s. It basically tells us everything that is not the Indian plate, basically. Okay, so we have the Himalaya. Anything where the Himalayan ranges stop, anything north of the Himalayan range is described as Trans-Himalaya. Trans-Himalaya is not a geologic term; it's more like a geographer's term, or maybe like a overall. It's a very broad term. It's not a geologic term. So, but if we think of the Indus Basin, yes, it's in the Trans-Himalayan region. Okay, I generally don't use the term Trans-Himalaya because it does not has much geologic origin. But the Indus Basin is north of the suture or north of the Himalayan range. The Himalayan range stops where the Tethyan Himalaya ends, basically at the Great Counter Thrust. So anything that's north of the Great Counter Thrust is Trans-Himalaya. So by that definition, Indus Basin is within the Trans-Himalaya. as for the Tethyan sediments or the Greater Himalayan rocks, there has been a lot of research in southeast or South Tibet regarding exhumation ages, and the cooling history is because especially in the Greater Himalaya, because those are much deeply buried rocks, those are metamorphic rocks, the cooling histories use other techniques. But in general, what we see is the Greater Himalaya exhumation also happened at about the same time as the exhumation in the hinterland or in the suture zone region. Okay, so it could be, if we think it in terms of like a critical wedge, we have the forethrust and the backthrust region. Both were evolving the Himalayan wedge at about the same time in the Miocene time, and were exposing or burying the rocks or exposing the rocks that were deeply buried under the surface. Okay, but this is a very, what I am saying is just speculation. There has been no research that says like we see like evidences of this happening, but no, I don't think like there is like extensive research that talks like, okay, this is happening because both the forth thrust and the back thrust regions were all happening at the same time. But there is some speculationary or like speculatory evidences that we can use to envision such a scenario. But in general, the Greater Himalayas were much deeply buried, and so the rate at which they came up is much faster than the rate at which the Indus Basin rocks came up. So there are some differences in the styles of exhumation or the styles of how the rocks were exposed. As for the Tethyan Himalaya, there is not much exhumation age data from Tethyan Himalaya in northwest India. But in southeast Tibet, we can see like very similar patterns of exhumation age data from the suture zone and the leading edge of the Tethyan Himalaya. So it's basically all happening across the India-Asia plate collision zone, just a bit north and just a bit south of the suture, and it's happening all over the region from 2000, extending from 2,000 kilometers from northwest India to about southeast Tibet.
Nice explanation. So moving towards the next question, another participant, Arnab Sil, is asking, would you please say the application of the helium dating technique and how is it related to thermochronology?
So helium dating, so what I like, the method is known as helium thermochronometry, the method itself. So if you break down the word, therm means temperature, chron means time, metry means measuring. So we are measuring the helium time temperature information. So that is the method name. Thermochronology is basically the overall study. Okay, so the study involving measuring the time temperature, history information. Okay, so if I'm writing the methods portion in a chapter, I'd use the term thermochronometry. If I'm doing a broad study involving all these thermochronometric techniques, I'd say like I'm doing a thermochronological study. Okay, so they essentially mean the same thing. Thermochronology is time, temperature, logy is study. So if that explains the difference between thermochronometry and thermochronology, I don't know if is that what the question asked, right?
I think the participant was keen to know something about helium dating technique.
Yeah,
So would you say something?
so helium dating, I can show like this present. Okay, I can show. So this is what is happening. So helium dating. Okay. So this is what is happening. So this, let's say like this is a zircon crystal. Okay, it contains some uranium. Okay, once the crystal has formed, the uranium that has been initially incorporated in the crystal as a trace element, the uranium starts to decay. Okay, it produces lead and alpha particles, thorium. It also produces lead and alpha particles. So these alpha particles start accumulating inside the crystal structure. This accumulation of helium inside the zircon crystal structure is very much dependent on temperature. Once a certain temperature is exceeded, all the helium that has been accumulated will diffuse out of the crystal. Okay. If the crystal again comes back to a lower temperature, it will again start retaining the helium inside its structure. Okay. So what helium dating does, it basically tells us when was the last time a mineral was at a particular temperature, which is called the closure temperature. So this closure temperature for zircon helium is about 200 degrees Celsius. Okay. So if I have a zircon crystal that, let's say, it formed at about 400 million years ago, okay, and it was sitting inside the crust, but for some reason it got metamorphosed to like 700 degrees Celsius. So if this zircon crystal is heated to 700 degrees Celsius, all the helium will go away. No helium will be left behind. Now, due to various other geologic processes, slowly over time, let's say this zircon crystal is coming back up towards the Earth's surface due to faulting or other processes. So once it comes back to 200 degrees Celsius, from that temperature onwards, it will start retaining the helium inside its crystal structure. So from 200 to 150, 160 degrees Celsius, right up to 0 degrees Celsius, it will start keeping the helium inside its crystal structure. So what we are measuring when we are measuring the helium age is basically the amount of helium that had accumulated in the crystal structure since the mineral was at a temperature of 200 degrees Celsius. So that's what we mean by helium dating, if that answers the question.
Yes, I think this answers the question. Okay, so moving forward, participant Saji Sahadevan is asking, did you go for minerals from both sedimentary and metasedimentary rocks for your study?
Yes, so the rocks that I mostly studied were they showed varying degrees of recrystallization. So some of them are like not like I would call them like pure sandstones. They're more like meta sandstones. Okay, and the temperatures did exceed to like about 240 to 280 degree, even up to 280 degrees Celsius in some of these rocks. So, and these temperatures are also confirmed by other studies like vitrinite reflectance, elite crystallinity, for example, from the region. But those were like from only one or two samples. This was a much large scale study with many samples that kind of confirmed some of the estimates by other studies.
Okay, okay. So one thing I'd like to mention for all the participants, you have already seen that how Gaurav is answering all the questions so elaboratively. So you don't feel shy to write him back if you have any other doubts. And whenever you wish to learn something or discuss something about thermochronology, you can always write to Gaurav or write to us. We'll get you in touch with Gaurav and try to get the answers. Okay, I think many of the questions will not find a conclusive answers here in a short duration. So if you wish to continue the discussion that initiated here also, then also you can go for that. Write mails to Gaurav and keep discussing and keep the discussion alive. Okay, so with this, we will now move towards the last question for today. Okay, our participant Anushka Roy is writing how biotite and muscovite preserve age. They have a tendency to be metamorphosed.
Yes, that's a very good question. So for biotite and muscovite, we do not use uranium and thorium. We use argon techniques. Okay, so it's not always just uranium, thorium, helium thermochronometry. We call it argon-argon thermochronometry. Okay, so argon is a good element to analyze when it comes to biotite, um, muscovite, or hornblende. Now, yes, biotites and muscovites, they have the potential to degrade over long periods of time. Okay, so it depends on what kind of information I am exactly looking for. Okay, so usually when we do like thermochronometry, we just don't do like one or two thermochronometers. We use multiple thermochronometers. Like I used 4 thermochronometers. So typically, if a researcher using argon-argon thermochronometry, they'll also use an additional thermochronometer like uranium lead zircon. So these provide like the boundary conditions. Each of them have different temperature. argon biotite is, I think, 350 degrees Celsius. Argon muscovite is 350. Biotite is around 450. Hornblende is around 500 degrees Celsius. Okay. There is a lot of complications when it comes to doing argon thermochronometry because of the factors that Anushka mentioned, like they are degradable. The rate of retention can fluctuate a lot. So we have to date more grains compared. So for zircon dating, we can just date like 5 grains from a sample. For argon dating, we usually do like around 100 grains. Not all of the grains will all be degraded at like the same quality, but we'll get some information. When we have this age information, we can actually model the time temperature histories and take the error into account of like how much degradation can affect it. We have ways to quantify that, like how can material degradation actually affect the age of the rocks. There are processes, techniques, and models that can account for the argon loss that can happen due to material degradation. So it's a very good question, and that's all I can say about that. Yes. Mhm.
Thank you. Thank you. Uh, Excellent answer to a very good question, what I can say. Okay. So, as I mentioned earlier, that all the students get in touch with Gaurav if you want to discuss something more. And within a while, this video will be available in our YouTube channel. So, all you can do is that share this with all other known connections and check out whether uh, they can also learn something from this lecture as well. And with this, I would like to gradually move towards a conclusion part of today's seminar. I thank all the participants for being there and asking some nice questions. And obviously, I thank Gaurav for this excellent seminar. I hope we'll meet again. We'll keep on discussing via emails and chats. Okay. That's all for now.
Sure, sure,
See
I'm
you again.
available.